Hello friends, in the last lecture we already saw the basic definitions of the antenna as well as the types of antenna and the performance parameters of the antenna. The different performance parameters that help us to select the specified antenna for the desired application. And now in unit number 2, the particular detailed analysis of antenna we need to be understand one. So today unit number 2, radiating elements and arrays, and topic name is the comparison of various radiating element. Now the content of unit number 2, comparison of various radiating elements such as infinite simal dipole, small dipole, finite length dipole and half-wave length dipole. The second part is that analytical treatment of these elements and comparison of various radiating elements. Third part is that types of arrays, 2-element arrays, n-element arrays, uniform amplitude, uniformly spaced, linear broadside and end fire array. And lastly, the planar, log periodic and Yagi-Uda antenna. For unit number 2, the reference books are number 1, C.A. Balnis, Antenna Theory, Analysis and Design, John Willey publication. Another book is that K.D. Prasad, Antenna and Wave Propagation, Satya Prakasha, New Delhi. Now basically in the analysis of radiation problems, the usual procedure is to specify the source and then require the field radiated by the source. So here again the Maxwell's equation are revisited over there. So these are the 4 Maxwell's equation we are using one, and for the analysis of radiation problem we need to be understand the particular source over there. So this is the contrast to the synthesis problem where the radiated field are specified. We require to find a particular source. If very common practices in the analysis procedure to introduce auxiliary function known as vector potential. So here we need to be understand first the source properly, which have the specified component J and M, which have the specified electric source J and the magnetic source M. Now at the time of calculating the radiated fields over there are 2 ways over there. So through the path 1 we are directly integrating this part, source part, to get the proper radiated field in terms of the electric field as well as the magnetic field. Whereas another procedure is that to understand the source properly, and then we are going for the integration of that to get the auxiliary function, that is the A, which is called as a magnetic vector potential, and F, which is called as a electric vector potential. So these auxiliary functions, once you get it, complex auxiliary functions, once you get it, then we need to go for the differentiation of that. So this is another part we get it to analyze the particular radiated fields over there. Then these are the particular equations available. Electric source J is not equal to 0, whereas the magnetic current source is 0. That time these equations you get it, and the 2 more important equations we need to be understand, that is the A is the magnetic vector potential, which is most important one, and the H of A. Whereas if the source is a magnetic source where J is equal to 0 but M is not equal to 0, then we go for the electric vector potential F, which is most important to calculate the value of that, and based on that E of F that we need to be observed one. So these 2 equations will always be used for the particular analysis. Then the specific dipole antenna, we know very well that the moment of the free electrons on the conductor representing the transmission line and the antenna. In order to illustrate the current distribution on a linear dipole, let us first begin with the geometry of lossless two-wire transmission line. The moment of charge created on a traveling wave current of magnitude I0 by 2 along each of the wire. When the current arrives at the end, undergoes complete reflection of 180 degree adjoining half cycle, hence radiation from individual wire occur. But the two-wire balanced transmission line, the current in half cycle of one wire is of the same magnitude but 180 degree out of phase. In addition, the spacing between the transmission line is a less one, so field get cancelled and no radiation takes place in the transmission line. In another figure, we can see that there is a flared component is available. So this is the part of transmission line where the source is feeding one and end of the transmission line is opening one. In a flared, the field radiated by one do not necessarily cancel those waves, and it will be moves from the positive charge to the negative charge. Okay, and that's why there could be the radiation possible in that case. The proper arrangement of the antenna is that, which is normally called as a dipole antenna, where the current or the signal is feeding at the transmission line and a particular end are separated properly. Then the charge is moving on from positive charge to negative charge, and hence the maximum radiation can be possible in that case. Now there are different types of antennas, we get it over there. One is called as an infinitesimal dipole, which is very small type of antenna, and this antenna we need to be understand thoroughly so that the other antenna analysis can be easily calculated from the theoretical antenna infinitesimal dipole. Then another one is a small dipole whose length is between the lambda by 50 to lambda by 10. Third one is the finite length whose length is lambda by 2 to lambda, and last one is the half wave length, that is L is equal to lambda by 2. Now the current distribution of a dipole, in that we know the transmission line equation. So current distribution along the open transmission line is I of z comma t is equal to real part of 1 by z0 a1 e raised to j omega t minus beta z minus a1 e raised to j omega t plus beta z. This is equal to this complex term will be converted in a trigonometric term. So 2 by z0 a1 sine of omega t sine of beta z. So if we observe the length of the particular antenna which is in between 0 to L, then my I of z will be I0 sine of beta in a bracket L minus z bracket complete. Whereas if the length is minus L to 0, then the I0 sine of beta in a bracket L plus z, we get it the equation. And if we put it a 0 value, then we get it the maximum amount of current I0, which is the maximum possible current. 0 at the end of the pole, I0 sine beta L at the feeding point, a periodic function with the period equal to the one wavelength, we get it. Then the different comparisons of the dipoles, we can see lambda by 10, lambda by 2, lambda and 1.5 lambda. The current distribution in lambda by 10 is a trigonometric, whereas in lambda by 2 is the properly moving one from one point to another one over there. Maximum current flowing through the circuitry. Then lambda is again the maximum current. 1.5 lambda is in that also we get it a maximum current. Now radiation pattern in both the direction of the dipole, we are getting it a particular patterns over there. But in that case the directivity is very less one, and half power beam width is 90 degree, and the input impedance is very small, that is the 2 ohm, and the behavior is the capacitor type. But if you consider the lambda by 2, Then the particular around the antenna in the both the direction, the directivity is more 1.64, and half power beam width is the 78 degree, and the input impedance is purely resistive, that is 73 ohm. Whereas in case of lambda, the directivity is more and more 1, and at the same time half power beam width is less 1. So 2.4 is the directivity and 47 degree is the half power beam width. Then for 1.5 lambda, directivity is 2.3, half power beam width is not applicable one, and it is purely resistive 100 ohm. So this is the comparison between the all types of the antennas. Now there are some steps we need to be observed for the particular radiation field. So first one, we need to define the source properly, whether it's a current source or magnetic source. Then write the expression for retarded vector potential either in terms of A or F. Then determine the retarded vector potential. Then convert A bar to the spherical coordinate system, which is normally required over there. Then determine H bar. Then determine E bar, that is the magnetic field as well as electric field, and then determine the E into H component. So this gives us the how much amount of the power radiated by the electric and the magnetic field. So these steps must be followed for the each calculation. Okay, thank you very much.